Welcome to all of you in the next lecture of this course. The summary of last lecture of my course was that it means that we were not able to find E convolution identity which belongs to L1R space such that this is satisfied. So, there does not exist. Okay. So, because using the convolution theorem we prove that there does not exist a convolution identity for which this is true. Okay. This is a convolution operation, that is why E is called convolution identity. Because using the convolution theorem, if convolution identity exists, there was a contradiction with some assumptions. So, that is why there does not exist a convolution identity. If it does not exist, what is the next point to think? I will tell you that we can say that okay, convolution, if we are saying E belongs to L1R, so of course it is a function which we have anyway said that it does not exist. So, now we are taking the concept of a function to the next level, which is called generalized function or distribution. What is that concept? All of you must have already studied what is a direct delta functions. Let us recall what is direct delta function. Direct delta is a function which is non-zero only at one point. Okay. Rest where it is 0, moreover it is satisfied this property. Okay. So, integral is equal to 1, that is the definition of a direct delta function we see. With respect to signal analysis, the same function is called unit impulse function. Unit impulse function. Okay. So, now and this direct delta function, because we cannot think of any function which is non-zero only at one point, is still its area under this integral is 1. So, we cannot think of, that is why it is called generalized function or distribution. Function or distribution. It is not called a function because if you look at the function property, these kind of property will not be there. So, we have extended the concept of a function to a generalized function. So, with this extended concept of a function, I can say that direct delta function will satisfy this property for of belongs to L1R. So, this is a direct delta functions. So, but this is, as we are saying, this is not a function. So, what is our next step? We will think of functions which could approximate this direct delta function. We will think of those kind of a functions which will approximate this direct delta function, because if we cannot achieve this function as such, means convolution identity as such, because this is not a function at all. Something is better than nothing. So, we are thinking of approximation of this generalized function. Okay. So, that is our next goal, how we could think of approximating this convolution identity. So, for that reason our aim is to define approximation of convolution identity. Okay. So, for that purpose, first I am defining a Gaussian function. Okay. What is a Gaussian function? All of us are aware already what is a Gaussian function. Gaussian function is basically I am writing in the form of let us say A, E, Okay. This will be the form of a Gaussian function which contains 3 parameters a, b, c. What is a? A will determine the height of the peak, b will determine the position of the peak, and c will determine the width of the peak. These are 3 parameters to govern the Gaussian function. I will show you that Gaussian functions in the figure also, how it looks like. But first of all, just for simplicity, we are taking 3 a, b, c, everything we are writing in the form of some one particular parameter. So, for that purpose I am taking a is 1 over c under root pi and c is 2 under root of alpha, okay, and b is 0. These are the 3 parameters I am taking. A is this. So, with this what this will become? I am denoting with E alpha x, A is 1 over 2 under root pi alpha e to the power minus x, b is 0, c, and c square will become 4 alpha. So, this will become my Gaussian function for alpha greater than 0. So, now if you wanted to see this Gaussian function for different value of alpha, that one could observe in the following figure. So, you look at here, what is the value of alpha? Alpha is 1 by 2j I am taking, and then we are taking the different value of j is 0 to 1 to 5. Alpha, what is the value of alpha we are taking? We are alpha is equal to 1 by 2j, 2 to the power j. So, what you could observe from the figure, that as alpha is tending to 0, means alpha is 1 by 2 to the power 5, this width of the peak is decreasing, and you could see as I am keep tending alpha tends to 0, what will happen? It will converge, it should converge to a delta function. That is my motivation behind defining this approximation of a convolution identity. That also you could see from here. This is the figure I have plotted for alpha is equal to 1 by 2 to the power 15. So, really alpha is tending to 0. So, you could look at this will look like a non-zero value only at a single point, and even you can work for a smaller alpha also. So, what is we could observe from these two figures, that as alpha tends to 0, this Gaussian function is tending to delta function. Okay. So, now let us now the another thing we wanted to observe, what will be the Fourier transform of this Gaussian function? What will be the Fourier transform? E to the power minus I omega x 1 over 2 pi alpha e to the power minus x square by 4 alpha. Okay. If you remember, when we were discussing about Fourier transform, we computed the Fourier transform of a Gaussian functions. Okay. So, with that knowledge I am directly writing here, which can be a question for the assignment also, e to the power minus alpha omega square. So, this will be the Fourier transform of a Gaussian function. So, that is the and that is one of the reason we are choosing a Gaussian, because the Fourier transform of Gaussian is again a Gaussian, not same Gaussian, but with respect to different width, magnitude, but the form of this is also a Gaussian. That's why we are choosing Gaussian function. So, whatever we have summarized in this discussion, I am writing in the form of one theorem, that if f belongs to L1R, then f convolution with E alpha as alpha tends to 0 plus at every point x where f is continuous. Okay. So, I have stated this theorem without proof. If anyone is interested to look at the proof of this theorem, it is given in the book of Charles K. Chew by Academic Press. So, what is the statement of this theorem? That if function is in L1R, then f convolution with E alpha, which is a Gaussian functions, will be equal to f x at every point x wherever f is continuous. The main point which you should note as alpha tends to 0 plus. So, basically the conclusion of this theorem you can also write that E alpha tends to delta on C collections of continuous functions. Okay. Collections of a continuous functions. So, this E alpha is called, because from here we have proved that E alpha will tends to delta on a collection of a continuous function as alpha tends to 0 plus. So, that is why E alpha we are calling as a approximation of convolution identity. Convolution identity. Okay, so that is what we have proved. We could not think of a function which can act as a convolution identity, but that is why this word is there, because as alpha tends to 0, because Gaussian is not defined for alpha is equal to 0. So, this is an approximation of a convolution identity. So, the next theorem we could write that if f belongs to L1R such that its Fourier transform is also in L1R. Why I am stating this? Because it is not necessary that if function is in L1R, its Fourier transform is also in R. We have already seen this when we were looking at the Fourier transform examples. We have found one example where in fact I have shown you that for some function belongs to L1R, Fourier transform was not in L1R. So, if so that is why we are making assumption function belongs to L1R such that Fourier transform is also in L1R. Then I can define the inverse Fourier transform of this function. Okay. So, this will true at every point x where f is continuous. Again I have stated this theorem without proof. If someone is interested to know about the proof, again the proof is in the book of Charles K. Chew. So, for detailed proof you can look at there. So, now this is the how we have defined the inverse Fourier transform. So, now this was about the L1R function. So, can we talk of any better space where we do not need to make a assumption that if function is belonging to that space, its Fourier transform is also in that space. So, for that reason we are taking this, if function belongs to L2R, its Fourier transform will also be. So, now the if f is in L1R, to talk about the inverse Fourier transform, I am saying f at should also be in L1R. So, can we talk of any better space where we can say that inverse Fourier transform always exists? Yes, the answer is yes, and that better space is L2R space. So, if f belongs to L2R spaces, it is always guaranteed that f at will also be in L2R. One could check this. If function is in L2R, Fourier transform is also in L2R. R. So, it is not just true, there is something more which I can write down in the form of a theorem, and that theorem says the Fourier transform is 1 onto map from L2R space to L2R space. It means for every G belongs to L2R, okay, there exists one and only one F belongs to L2R such that this condition will be satisfied. Okay. So, that is the idea, that Fourier transform is a 1 and onto map. It is in fact something more can be said for this, and what is more, we have already studied Parsable relation when we were discussing the Fourier series. Now, Parsable relation is also true in case of a Fourier transform. We will be using this relation later on in the form of a inner product, that is why I have stated this here, and this is called Parsable relation. Okay. Because you can also write this as a inner product, because L2R is a Hilbert space, so always you can define the inner product. So, the theory of the Fourier transform of a function which belongs to L2R space, there is a elegant theory, and that theory is called Plancherel theory. So, one could study this theory in the course of a harmonic analysis, that how the Fourier transform of a L2R function behaves, Fourier transform is in L2R, as well as this Parsable relation is satisfied, and many more. So, that is the beyond the scope of this course, that one could see in the course of a harmonic analysis, but that is just because I will be using this relation later on, that is why I have stated here. So, now what was the sequence we followed to define the wavelet? First we did some mathematical foundation, then we defined the Fourier series, then we defined the Fourier transform, and we were just recently we were talking about the Fourier transform, and now I am going to the next thing, which is called time frequency analysis. Time frequency analysis. Time frequency analysis is a branch of a signal analysis to look at the signal in both in time domain and in frequency domain together. So, time frequency analysis is a branch of signal analysis to analyze the signal in both time and frequency domain together. So, of course, if from the Fourier transform also we can analyze the signal in both time and frequency domain, and now we are introducing another concept, time frequency analysis, which is also used to analyze the signal in both time and frequency domain together. So, of course, then I have to state some of the disadvantage of the Fourier transform. That is why we are going in this direction. So, with couple of disadvantage of Fourier transform I am mentioning here. Disadvantages of Fourier transform. In a short form I am writing FT are as follows. What is the first disadvantage one could think of Fourier transform? Any idea you could think for a while? Because if you look at the definition of Fourier transform, which I have again recalled here, of course this is over R minus infinitive to infinitive. You need complete information of this function for a mathematicians, or if you are saying signal. So, you need, for as an engineer, you need complete information of this functions. In fact, if you do not know any future behavior of the signal, that also you know, you should know to compute the Fourier transform. So, that is that can be considered as one of the drawback, that you need complete information of the signal. That is the first drawback. Second drawback is, again second drawback I am mentioning with respect to definition itself. If fx is changed in a smaller neighborhood, sometime like if signal is changed, I could if signal is changed only by small magnitude as well as in the small neighborhood, but you know this Fourier transform will be changed entirely if you look at the definition. So, complete spectrum is changed. So, basically Fourier transform is not based on the local information of the function, it has complete, it should have complete information, which is also the second drawback of the Fourier transform. So, third drawback you could think that if you look at if signal is periodic, we can take Fourier series. If signal is infinite, signal is of infinite period, then we could think of Fourier transform. But mostly real life signals are neither periodic nor infinite. You could observe mostly signals what we see in the real life. If any signal is coming from the musical instrument, so that's neither they are for a very short period of time. So, neither they are infinite. Moreover, if you must have, definitely you must have heard some signal of the musical instruments. So, they gradually increases and then they gradually decay. So, they are neither infinite as well as neither periodic. So, this also motivate us for a time frequency analysis, because these type of signals you cannot handle with the Fourier transform. So, again in a nutshell, why we are going in the time frequency analysis directions, because a couple of disadvantage of Fourier transform, that you need complete information of the function. Moreover, if function is changed in a smaller neighborhood, complete spectrum is changed, which I have said as a disadvantage number 2. And the third disadvantage is that to define the Fourier transform of Fourier series, I should have either function is of periodic of finite period or infinite, while real life signals are not that. So, because of that reasons, there was a scientist D. Gabor who discovered Gabor transform in 1946. So, first he observed the drawback of Fourier transform and then he introduced a transform which is called Gabor transform. Okay. So, before going to the definition of a Gabor transform, let me introduce the concept of a window function. What is window function? A function which is in L2R such that x wx will also be in L2R, then it is called window function if it satisfies both the property. This one means it should be in L2R as well as this property. So, what is the implication of this property on a square integrable function? Implication of this property, if you observe, if you know how the behavior of this function, if it x is also in L2R, it means that it will decay faster, as if you just take only this property. If you do not consider this second property, you consider only square integrable function, then what will be the comparison? A function which is satisfying this additional property will decay fast, and that is why you know this is called a window function. It has a resemblance with the window which we see our in every room, because window are, you know, they are, we call it as a window because it is in the smaller part of the wall. Otherwise, we do not call it as a window, we call it as a wall itself or door itself. So, that if you borrow that idea of a window, with that idea it is defined as a window function. So, because it will decay very fast. So, can you think of any example which will qualify the properties of a window functions? Of course, one of the example which we have been keep doing is a Gaussian function. Gaussian functions will be a window function because you can see it belongs to L2R as well as this property will also be satisfied, and otherwise with the property whatever definitions I have given, otherwise if Gaussian functions also decay very fast. That is why Gaussian functions falls in this category. So, if it decays very fast, so we are defining two notions with respect to this window function, and what are those two notions? Two notions are I am defining the center and radius of the window function. So, center of the window function will be defined by this formula which I am stating now. Okay, and radius will be defined by this formula. Okay. So, that is how we have defined the center, and that is how we have defined the radius. So, what will be the width of the window function? The width of the window function will be 2 del omega. Okay. So, now it is clear to everyone that how we define the window function, and as I said that we will be needing this concept to define the Gabor transform. So, Gabor used this definition of a window functions to define the, so when he defined window transform, he took the particular example of a window function which is Gaussian, as we are keep saying. So, Gabor used Gaussian function to define Gabor transform for alpha greater than 0. So, if function belongs to L2R, I am giving you the definition of a Gabor transform Okay, so, this is the definition of a Gabor transform which you could see from here. Here we have used E alpha as a Gaussian function, which is a window function. Later on I will extend this idea of a Gabor transform to find to window transform, but this time we are taking some particular example of a window function which is a Gaussian, and that is why this is called Gabor transform. So, Gabor transform. So, if you look at the right hand side of this Gabor transform carefully, what do you observe from this? So, you could observe that E alpha, which was qualifying the properties of a window functions, it is localizing the Fourier transform this way. Okay, it was localizing the Fourier transform, which was the drawback of a Fourier transform, as I have just stated few minutes back. So, it was removing the drawback of the Fourier transform. So, now you could, because we know this is the property of a Gaussian, I am just writing x minus b is equal to t. Okay, so, this will be equal to 1. Okay. So, if this property is true, if I am integrating this with respect to dB, this will give you f at omega when omega belongs to r. Okay. So, you can also observe this results very carefully, okay, that basically if I am integrating this Gabor transform with respect to this B, then I am getting this Fourier spectrum. So, it means that Gabor transform is localizing the Fourier transform around x is equal to b, around x is equal to b. So, now if you look at this, what will be the, if I am asking you what will be the center of a Gaussian function? Center of a Gaussian function, if in my previous slide, this is the definition we have used for a defining the center of the window function. So, what will be the center of a Gaussian function? That you can take it as an exercise. The center of a Gaussian function will be 0 and the radius of a Gaussian function will be del e to the power alpha will be, that will be the question for your assignment, that radius of a Gaussian function is under root of alpha. Okay. That is your assignment question. Okay. So, now again I am restating the definition of a Gabor transform in this way. I can write because E alpha is a real function. So, that is why this thing I am writing, so that I can write in the form of a inner product. Of course, you should make a difference, this is a omega and this is a w function. W is the notation which I am using for a window function. So, Wx will be equal to e to the power I omega x. Okay. So, now you could use the Parsable relation which I have stated earlier. Using that relation we can always write this thing. Okay. So, for that reason we have to compute the Fourier transform of this window function. What will be the Fourier transform of this window function? Of W, of course, I am this time I am taking eta because omega is already here. So, this will be e to the power I omega x e alpha x minus b with respect to dx. Okay. So, by rearranging the terms, I can write down this, and then by substituting x minus b equal to some parameter, what is at the end, I can get that w hat eta n will be equal to e I b eta minus omega e to the power minus L omega. So, this is the best part of Fourier transform of a window function is that this is also a Gaussian, as I have already said that the Fourier transform is of a Gaussian function itself is a Gaussian with different parameters. So, that is what we are getting this, and that we can write down again in this form. Okay. So, you could observe the signal in both the domains, in this domain, in this domain. So, any function which you want to use in time frequency analysis, what is should be the assumption that w should be a window function as well as w hat should also be a window function, and we have a plus point with the Gaussian, because Gaussian is a window function and its Fourier transform is also in the form of a Gaussian, which will again be a window function, and that is one of the reason that Gabor found that Gaussian will be the best example to choose as a window function initially. Because so any function which, or you could say which function you should choose in time frequency analysis, you should choose a function when w should be a window function, moreover its Fourier transform should also be a window function. That is the idea. So, now we will extend this idea of a Gabor transform to define window transform, Okay, that I will do in my next lecture, how to extend the idea of a Gabor transform to define window transform when you are not choosing as a special window function like Gaussian, when you are choosing any general window function which should satisfy these two criteria. Okay. So, thank you very much.